Hello everyone. My name is Xuan from Johns Hopkins University. So my topic today is template model reviews mechanism of self-writing of a cockroach expelled robot. So first, let's look at cockroach self-writing. From the animal video, we find the cockroach keeps opening and closing its wings and tries to somersault, but very often it cannot simply do that. Instead, it flails its
I'm
legs side.
sharing the screen. I can't see the slides still.
Yeah, I'm sharing.
Can you see it? Can anyone else?
At this time, I don't see the slides. Oh, now they showed up.
Just come on. Okay.
Oh, okay. Oh, okay. So we can see the self-writing is a strenuous task for the cockroach. During self-writing, the total gravitational potential energy first increase, then decrease. And we name the energy difference here is the energy barrier. Although the cockroach keeps inject kinetic energy into the system by both wing and leg oscillations, the cockroach cannot self-write quickly because there are energy dissipation in the meantime. So how to accumulate the inject energy to overcome this energy barrier is important in self-writing. To understand the self-writing mechanism of cockroach, in our previous study, we built a wing self-writing simulation robot.
So again, the slides are not showing up.
This one?
Cannot see. Okay, now it's.
Oh, okay, sorry. So so just like cockroach, the wings keeps opening and closing its wings, and the leg keeps flating from one side to another. There is a time delay between two oscillations, and we use a phase to represent it, which equal to the time delay divided by the leg oscillation period. From our previous study, we find an interesting result. Although the phase doesn't change the oscillation amplitude, it will influence the self-writing result by changing the coordination between wing and leg. In this figure, the white means success and black means failure. And we can see the white area is concentrated around 0 and 50%. The black area is around 25 and 75%. We name them good and bad phase respectively. To figure out the phase and further understand the mechanism behind self-writing, we built a template model. Template is a simplest model that captures most fundamental dynamics and which helpfully explain the mechanism, review general principles, and be useful in robot design control. Here is a template we abstract from the winged self-writing robot. During leg flailing, the robot mainly rolled in the front plane, so we simplified it into a 2D plane. Because the mass of robot is mainly concentrated around the body and pendulum, so we approximate leg and the wings are massless links, and body and pendulum are point mass. We also approximate wing-ground contact is a point contact. Wings can slide on the ground and rotate around the wingtip. We also approximate the wing-ground collision is instantaneous and inelastic. Finally, we approximate motors accelerate and decelerate instantaneously. Based on template, we can first calculate energy barrier from its geometry. The yellow dot is the center mass during self-writing. It reaches the highest during self-writing and when it crosses vertical line. And the increased potential energy to reach there is the energy barrier. We can use the lifted height delta H to calculate it. From model calculation, we see for the robot with larger wing angle and larger leg angle, the energy barrier becomes smaller. After wing fully open, the robot is trapped in this energy local minimum at the beginning. Energy injection from wing and leg will help it to reach the local maximum and finally self-write. But there is energy dissipation in the meantime, like collision, like motor stop. So we need to calculate energy budgeting for it. To calculate energy, we need to figure out the dynamics of system. Even though the system is simple, it is a hybrid dynamical system. As we mentioned before, the velocity is discontinuous, and the contact between wing and ground is hybrid. The contact could be fixed contact, sliding contact, no contact, or collision. We divided the motions of this hybrid dynamical system into two types, continuous motion and discrete events. Here we can see there are 6 different cases, and each of the cases are governed by different equations of motion. We'll elaborate this one case as an example to show how we deal with these dynamics. It is a robot collision with ground during leg rotation. At this moment, there are 3 external forces: gravitational force, normal force, and frictional force. First, we approximate collision is instantaneous. So the normal force and the frictional force is much larger than the gravitational force. So we can neglect it. Second, because the center we choose a center of rotation at contact A, so there is 0 moment arm. So these 2 forces, there is no torque. So we can have angular momentum at this moment. So we can write down equation to solve it. So we solve the dynamics for the one example, and we actually have done it for all possible situations. With the solved dynamics, we can model the evolution of system over time as visualized in top video. Below video is the evolution of the corresponding energy. The red dot shows the mechanical energy trajectory of the robot. The blue curve is its potential energy landscape, which is as a function of the body role is defined here. So energy is accumulated during wing opening and leg rotation. However, before crossing this energy barrier, energy is dissipated. So the robot falls back and rolls to the other side. And for this rolling, the cumulative energy is greater than energy barrier. So the robot successfully self-rights at this time. We use our template model to break down the cumulative energy into 3 contributions. First is the work done in the wing opening. After wing fully open, because of inertia, the robot still have the velocity. So we measure this kinetic energy as wing's contribution. Second is the energy dissipation when wing tip collide with ground. Third is the work done during leg stroke. And the leg stroke consists of 3 parts: start, leg rotation, and leg stop. From model, we calculate energy contribution for good and bad phases. We calculate work done in wing opening, the collision dissipation, and work done in the leg stroke individually for different wing and leg oscillation amplitude. There is a significant difference between good and bad phases, and especially in the work done by leg stroke. We calculate the cumulative energy by the above equation and compare it with the barrier to predict self-righting. We calculate their difference and here, and if there is a deficit, it means the robot will fail. If there is a plus, it will succeed. First, we can see the robot with larger wing and larger leg oscillation amplitude have larger energy difference. So this makes the robot easier to self-right. Second, for good phase, its plus region is much larger than the bad phase. So we can see with the good phase, the robot can accumulate more energy than bad phase, especially in the leg stroke. So it can help the robot easier to self-right. To further validate our model, we made a simulation by Chrono Engine. We add the thickness of robot, but keep other variables same with the template. By doing simulation experiments, we get self-righting results for good and bad phases, and comparing it with the model prediction, we found they match pretty well, and the mismatch could come from the model approximation. We have studied phase by template, but template can go beyond. It is predictive, so we can use template to do model-based control and design. Here is a preliminary result. We maximize work done in the leg stroke by controlling motor style moments. And we can see with the control, the self-writing performance is further improved. So see the summary of my talk, and I'll thank my landmates and funding, and thanks for your time. I'll take questions.
Okay, just time for a very quick question. We'll have the next one. Okay, if there's no question, next one, Xuan.